Alright, today we're going to talk about an application of Newton's law of gravity called surface gravity. How strong gravity is on the surface of a different planet or star or whatever. Alright, if you travel to a different planet, your mass would be the same, but your weight would change. Remember, mass is intrinsic. It comes from each of the atoms you have. It's just something that belongs to you as you were. But weight is the force of gravity due to the planet. Things on a new planet would accelerate at a different speed. We say the planet would have a different surface gravity than the Earth. It would still look like the Earth in that the gravity would be constant, and it would always point downward, and it would always be the same for every object, but it wouldn't necessarily be 9.8 meters per second squared. One way to envision this is to say that bodies create a gravitational field in the space around them, a quote-unquote influence on how things move when nearby. The freefall acceleration measures how strong this field is, so we sometimes also call g the gravitational field strength of the Earth at its surface. And in this model, we'll say that g is 9.8 newtons per kilogram, which is of course the same as 9.8 meters per second squared. I bring this up largely because the AP committee tends to go back and forth on these things. It's not entirely clear why, but sometimes they'll specify g in meters per second square, and sometimes they'll specify it in newtons per kilogram, even though those are really the same thing. We've been saying on Earth that your weight is m times the local gravitational field strength. So on the planet, g on the planet would be m, your mass, times g of the planet, where g is that acceleration of freefall. The law of universal gravitation says the gravitational attraction is due to the planet. So we'd have f sub big G of the planet, and that would be g m of the planet times mass of your object over the radius of the planet squared, right? Why the radius of the planet? Because that's how far you are from the center. Your height doesn't really matter on these kinds of scales. These two forces are really the same physical force, so they should be equal. So we have the mass times g of the planet is big G times mass of the planet times m over rp squared. Canceling out the masses, the mass of the object, as we often do, we end up with that the freefall acceleration, or the gravitational field strength, on the surface of the new planet has to be big G times the mass of the planet over the radius of the planet squared. We can do this to compare two planets by saying if we have planets 1 with m1 and r1 and planet 2 with m2 and r2, we compare their surface gravities by dividing this expression for each. In other words, we have g1 is this, and g2 is this. And then a lot of things cancel out because well, not a lot of things, but the important thing is the universal constant cancels out. We don't need any more. And we find that the ratio of gravities is the ratio of masses over the ratio of distance squares. This is most useful if planet 2 is the Earth. For instance, let planet 1 be a planet with twice the mass of the Earth, but only half the radius. And let planet 2 be the Earth itself. Then the ratio of the g on the new planet to g on Earth would be the ratio of their masses, which is 2, over the ratio of their distances squared, which is a half squared, or a fourth. And 2 over a fourth is 8. So such a planet would have 8 times the surface gravity of the Earth. Things would weigh 8 times as much, and they would accelerate 8 times as quickly when free falling. So let's try this problem. Planet X has freefall acceleration 8 meters per second squared at its surface. Planet Y has twice the mass and twice the radius of planet X. On planet Y, what will we say about the surface gravity? So we go back to saying gy is to gx as the ratio of their masses, my over mx, over the ratio of their radii, ry over rx squared. They say it has twice the mass, but also twice the radius. And then we're going to square the second one of those. So the ratio is 2 over 4. So gy should be 1/2 of gx. Since gx was 8, we should get 4. A 60 kilogram person stands on each of the following planets. On which planet is his or her weight the greatest? If we look at the first one, would have m over r squared with g. That's this guy. The second one would have 2m over 2r squared, which is 1/2 gm over r squared. so that's smaller. And this one would have g 3m over 3m quantity squared, or 1/3 g m over r squared, so smaller yet. So this is where she is, or he is, the greatest weight. Planet P is only half as dense as the Earth, but twice the radius. What is the acceleration due to gravity in meters per second squared on the surface of planet P? As a reminder, the relationship between density, radius, and mass of a sphere is that the density is the mass over the quantity 4/3 pi r cubed. We weren't given the mass of the new planet, we were given its density, so probably our first thing should be to get the mass, and then we can go back and use that formula we've been using. The mass of the planet is the density times its volume, right? We're saying here is that this is the volume of the planet. And the mass is the density times the volume. So if we put in things we know, we have 4/3 times twice the radius but cubed times half the density. And then we can pull out constant factors. So let's pull out the 2 cubed and pull out the half here. Trying not to. And what's left, and this is really important, what's left here, 4/3 pi r cubed rho e, that's going to be the mass of the Earth. So 2 cubed times a half is 8 times a half, which is 4. So we found out the planet is 4 times the mass. Now we can go back and say, well, remember that g of the planet over g for real is the ratio of masses over the square of the ratio of radii. So we have 4 over 2 squared. But 2 squared is 4. So we have that g planet over g is 1. Kind of bizarrely, this planet has exactly the same surface gravity as the Earth. This is a weird case, but why not? Weird cases can happen.